Okay, we're going to do section 23.3 and 23.4 today. And in section 23.3 we find that if I were to take the derivative of the arc sine of u, so u could be any complicated function at all, then I'm going to have 1 over the square root of 1 minus u squared du dx. And if I want the derivative of the arc sine, way to go, arc cosine, which I'm not spelling too well, of u dx, then that's going to be minus, really? Minus 1 over the square root of 1 minus u squared du dx. And again, if I look at the back cover of my book, I see that both of those functions are there, number 20 and 21 are my differential equation formulas, so it's not like I'm going to have to remember them, but I am going to have to think about what they look like so that when I take the antiderivative of something that looks like that, I can come up with the arc sine function. Oh, we have some more. So the derivative of the arctangent dx with respect to x u, 1 over 1 plus u squared du dx. And the derivative of the arc cotangent minus, boy, this is so predictable, 1 plus u squared du dx. I didn't realize it was this predictable. Oh, maybe I did. And then the derivative of the arcs. Now, you know, if you're taking the derivative of the arc secant, then you're probably working the wrong problem, right? I mean, that would be my view of the situation. And even the arc cotangent. There's only one problem in the physics book that uses the arc cosecant in the problem. Anywhere in the physics book, and I think there's only one problem that uses the arc cotangent. Now that's how often you would use that to solve a problem. So the derivative of the arc secant, and this is where you're going to get into problems, because now I got to take the absolute value of u. And now that complicates my issue a whole lot. Because as soon as it's not the absolute value of u, it's a negative number, then I'm really hosed. Arc cosecant. And why did I put a du there anyway? Anybody know that? Should be a dx. Minus 1 over the absolute value of u, square root of u squared minus 1 du dx. Okay, so that's the issue. Those are the formulas that we're going to have to know. Well, we're not going to know them. We're going to have look in the back of our book and use them from the back of the book when I solve the problem. So, because there's no reason to think that I'm going to remember them. I know I'm not going to remember them. Should we start with number 1? Okay, we'll start with number 1. Y is the arc sine of 5x. So y prime would be, and I'm looking at the formula on page 769, and I write 1 over the square root of 1 minus 5x squared times the derivative of 5x, which would be 5. So I would get rid of the 1 and put a 5 there, and I would be done. I'm not going to do that problem without having my book open to the right page, though, because I'm not going to remember what it is. Number 2.
Do we not need to solve these?
You are. You just did. That's all there is. There ain't no more. No, no. Can it be more complicated than that? No, it can't. It can't be any more complicated than that. In your Calculus 1 class, you're probably not going to remember those. You're not going to have them memorized. Y is equal to arc cosine 6x. Y prime. Again, I'm looking at the right page, and I have 1 over, I got a minus sign there, square root of 1 minus 6x, the quantity squared. The derivative of 6x is 6, so I change the 1 to a 6, and that's all there is. There ain't no more. That's why calculus is so much easier than college algebra, because it really is that much easier. Okay, so number 3, y is the arc tangent of 3x. Y prime. I don't have to turn the page back anymore because it's on top of the page. 3 divided by 1 plus 3x, the quantity squared. So that's my u. I stick it where the u goes, take the derivative of it, stick it on top. Joel, you're not asking me to explain anything. How come?
Well,
Too frigging simple.
Maple calculator.
Yeah.
Yeah, that's right.
Yeah.
How about you explain this next one? I should do it.
Let's see. Y is arc secant. Arc secant of 4x. Okay, so y prime, I look at the formula for arc secant, and I find that this is going to be 1 over the absolute value of u, which is 4x, times the square root of 4x, the quantity squared, minus 1. No, squared, you idiot. Minus 1 goes the other way. Squared minus 1 times the derivative of 4x, which is going to be 4. But then I'd put the 4 there and not put it over here. So I'm done. Is that good enough for you? Yeah, okay,
I do
good.
have one question.
Yeah?
Will the questions on the test also be this easy?
If they have to do with arc sine and arc cosine and arc cosecant, they certainly will. Unless you fail to open your book to the back cover and look to see what the formula is, in which case you will be totally, completely hosed. But yeah,
Okay.
the problem set is just as easy as these guys are.
I have a question.
Yeah.
Why is there a 4 on the top there?
Because the derivative of 4x is 4. So the formula says in the form 1 divided by absolute value of u squared root of u squared minus 1 times du dx. So the derivative of 4x with respect to x, derivative of 4x with respect to x is 4. And that's why there's a 4 on top.
Multiply.
Okay, number 5. There's some pattern here. I wish I knew what it was. All right, the y is the cosecant, arc cosecant of 1 minus x. All right, so I come back and say, well, y prime is equal to, I look at the arc cosecant, and I need a minus sign. I need a 1 minus x, the absolute value. I need the square root of 1 minus x squared minus 1. And then on top, I want the derivative of 1 minus x, which would be minus 1, which means those guys become positive. And that's all there is for that guy. Now, you could expand this and subtract the 1 if you wanted to, but why bother? There's no reason to bother. because there's a minus in the equation that I'm using, but the derivative of 1 minus x with respect to x is minus 1. Minus 1 times minus 1 is not minus 1 anymore. So y is the arc cotangent of the square root of x. Okay, so y prime is going to be arc cotangent. Okay, so I got a minus sign. I got 1 over 1 plus the square root of x squared times 1/2 x to the minus 1/2. Okay, so this guy probably would rewrite. And so I've got minus 1 over the square root of x times 2 times 1 plus x.
You necessarily have to write it in the test.
Is your name on the test?
Yeah.
How many did you miss before you got to that one?
Let's say I had
Buco many? Well, then it'd probably be marked right if you got buco many wrong already. If it was the only one that there's any red ink possible on, which would be totally impossible for that to be the case, but then we'd have to say no. Well, you wouldn't use a negative exponent in a final answer, right?
Why are you
So-
multiplying it by 1/2?
1/2?
Yeah.
All right, so if y is equal to the square root of x, then y is equal to x to the 1/2. So formula number 3 in the differential equation, the differentiation formulas say that if I want the derivative of it, I put 1/2 out in front, and then I go x to the 1/2 minus 1. So I write 1/2 x to the minus 1/2, and then I would rewrite that as 1 over 2 times the square root of x. Okay, good enough? Okay, that was number 6. Okay, looking at number 7. Is it okay if I do your problems too?
No,
All right.
not at all.
It's not okay? Why?
You're doing them anyway.
I'm doing them anyway. 3 arc cosine x minus 1 y prime. Now I got to go look at arc cosine, if I could spell arc cosine. All right, so I got a minus sign, I got a 3, I got a square root of 1 minus x minus 1, the quantity squared, and I'm done, because the derivative of x minus 1 is 1. So I'm done with that guy. Now the harder math gets, the easier it is. That's just one of those axioms. Okay, y is equal to 4 arc sine, yes, Joel, x to the minus 1.
Why is that negative?
Well, if I turn my page, go to my page to 767, I notice that the derivative of the arc cosine is minus 1 divided by the square root of 1 minus u squared.
That times the derivative, which is also negative 1.
No, the derivative of this guy is 1. The derivative of minus 1 is 0. The derivative of x is 1.
Oh, I apologize.
Oh, Joel was thinking, that is good. That is just such a good thing to happen. All I have to do is get William to think every now and then, and everything will be so wonderful. Yeah, I know. Okay, I'm looking at the derivative of the arc sine guy in my book, and I read, this is 4 1 over square root of 1 minus x to the minus 1 squared times the derivative of x minus 1, which is going to be 1 times x to the minus 2. And then I'd rewrite that minus 4 divided by x squared square root of 1 minus 1 over x squared. Yeah, that's probably what I would do. That's 8. Oh, if I go to 9, then I'm done with this section.
Okay. Just
Number 9.
Sorry.
Yeah, that's fine. Now, how did we get these guys anyway? We got them by using that limit formula. So in your advanced calculus class that you'd have your senior year as a math major, you would prove that these differentiations are correct. Okay, but in a calculus 1 or 2 class, you wouldn't. You just use them. And in a tech math pre-calculus type class, you just use them. All right, where was I? Number 9. I think I said number 9 already in the other page, didn't I? Y is equal to the arc cotangent of 3x squared. Okay, so y prime, and I've got a minus sign, and I've got a 1 over 3x squared absolute value. Now, the absolute value signs in that case would be optional. Well, x could be an imaginary number, right? So it could be. So I guess you're going to have to keep them there. Square root of 3x squared minus 1 times the derivative of 3x squared, which is going to be 6x. All right, so I would probably rewrite that y prime.
2 times.
Oh, there's got to be a 2 there. Yeah. So I got minus 12x.
Minus 12x.
There's a 6 here, and there's a 2 there, and there's a minus sign there. And 2, let me check my calculator. 2 times 6 equals, wait a minute, let me put it in octal.
13.
Octal. 2 times 6 equals 14. You're right, it's 14 in octal. Let me put it in hex. 2 times 6 equals, that's Charlie. That should be a minus C. Huh?
Could you just explain it as you go through it, how you're getting each number?
I do. I'm just waiting for somebody to pay attention.
I am paying.
Oh, okay. Well, are you somebody? All right, let's see, where are we? 9x to the 4th minus 1. I just squared the 3 and got a 9, and squared the x squared and got an x to the 4th.
Okay.
Good enough? All right, well, we're done with this section. So that's, oh, good. Now we get to do derivatives of the logs. Oh, that's even more. Now, the derivatives of logs are important. We're going to, you know, the derivative of the arc transcendental functions are things that are slim and far between for stuff, but the derivatives of logs are things that come up often in nature and often when we work problems. Yeah. No, you can believe that or not. I don't really care. Section. We'll find that out, right? 23, 4. All right, so if I want the derivative with respect to x of the log base b of u, again, this is a formula. You're just going to use it. I'm going to have 1 over u log base b of e, e being the 2.718281828, the base of the natural logs. Now, I guess I got that wrong. This is u with respect to u. It's going to be that. If I take the derivative with respect to x of the same thing, then I end up with 1 over u log base b of e times the derivative of u with respect to x. Okay. And then continuing. Now those two formulas are probably going to be used in this section of the book and never again in your life. But the next two formulas are going to be used often in your life, and that is that the derivative with respect to u of the natural log of u is 1 over u. And that derivative of u of x, derivative with respect to x of natural log u is equal to 1 over u du dx. Okay, now the issue is, why would we use the derivative of the natural log so often in solving problems, but not the common log? Okay, so that's the issue being raised by the second row. So here I got a circuit, and I've got a capacitor, and I have a resistor, and the voltage across the capacitor is Q over C, or C over Q? Yeah, Q over C, right? Q over C, and the voltage across the resistor is IR, and current is dQdt. Okay, so my voltage source is going to be my Q over C plus dQ dt R. All right. So now I've got a form. I have something in the form Q prime R plus Q over C, and I'm going to divide everything by R. So Vs over R is equal to Q prime plus Q over RC. Now, we have a formula that says that if I can get my differential equation in the form y prime plus px y is equal to qx, where qx and px are functions in x only, then y is going to be 1 over the integral 1 over e to the integral px dx integral qx e to the integral px dx. Yes, that's what we're doing. And so now here's a problem where we end up with e to some exponent. When we're gonna solve for what's in the exponent, we're going to have to take the natural log. Also, when I go and I do integration, when I do differentiation, when I say y is equal to x to the n, right? I say y prime is n x to the n minus 1, right? And then when I go the other way, if I integrate both sides of this equation, I end up with x to the n. All right, well, if y is 1 over x, and I take this guy here, what would n have to be? If I integrated both sides. and it would have to be 0, right? And I wouldn't have to get anything. So this becomes natural log x. When I take the integral of 1 over x, that becomes natural log x. And when I take the derivative of natural log x, I end up with 1 over x. So it's just one of those symbiotic relationships. I end up multiple times. I got a pond. I got a 100,000 gallon pond, and I got some water flowing into it with some salt in it. And I got some water leaving the pond. I end up having to use the natural log someplace in the solving of that problem, and I'm going to have to use the integral of the natural log or the derivative of the natural log sometime in the solving of the problem. So it goes over and over again. But common laws, law E, the base of the natural logarithm, something given to us by God, not by man. It's the nature of the world. It's the nature of nature. Capacitors charge as a function of E. They discharge as a function of E. Inductors do the same thing. Okay, so on and on and on. Lots of things do that. So when I jump out of the plane and I open my parachute, I'm going to have a function of E explaining my drag. Okay, now, when I look at petals on a flower, it's going to be some function of E. When I look at the growth rate of some bacteria, some function of E. When I look at that nuclear radiation particles decaying, it's a function of E. But when I look at common logs, base 10, the number 10 that we use was given us by the northern African people, the Muslims there, in 650 AD. It has nothing to do with nature. It has everything to do with us having a numbering system that makes sense. But when God created the heavens and the earth, he didn't do it using base 10. Okay? That didn't happen. He used it using the base of the natural logarithms, E. His choice. He was God. He can do whatever he wants, right? He could have done it based on base 10, right? And that bacteria will grow as an exponent of 10 instead of as an exponent of e to the 2 point whatever, e being 2.718281828. He could have done that, but he didn't. That's the difference. Does that make any sense? Yeah, see. So you have days like that. Okay, well now, what are we going to do? We're going to solve some more problems. All right, so, and again, if it's a natural log thing, I'm just going to do it because it's so easy. If it's a common log thing, then I'm probably going to have to look it up. So y is log 4x minus 3. Okay, so I go to the page with that on it. Okay, I'm looking at it. Y prime going to be 1 over 4x minus 3. Okay, and then I'm going to go log base 10 of E, log base 10 of E, the derivative of 4x minus 3, which is going to be 4, so I'll put a 4 there. Huh? I just put a 4 here.
Why?
4x minus 3. The derivative of 4x minus 3 is 4. So I'm going to multiply by 4. I'm doing exactly what the
That's in respect to x?
yeah, with respect to x, right. Yeah, so it says 1 over u log base 10 of E, then du dx. All right. Number 2.
Is that
Am I done? Yeah, I'm done.
okay? Sorry, that was respectful.
I got a quick
Yeah.
question. All right.
Now I wouldn't write 10 there because it's a common log, so I wouldn't have the 10 there.
It's already.
Yes, 10 is implied by not having anything, right?
Now, if it's in respect, how do you know if it's in respect to you?
Well, it wouldn't be. Let's see, what is that? Find the derivative of each function. So, number one, you have a dependent variable y. The independent variable is x. So it has to be with respect to x. There's no u in the problem.
Right.
Yeah, u is 4x minus 3.
Okay.
Yeah.
Okay.
Number two. Oh, now I did it. Still doing it. Y equals log x squared minus 1. All right, so y prime would be 1 over x squared minus 1, natural log, common log e, times the derivative of x squared minus 1, which is 2x. And then I'd probably rewrite that 2x x squared minus 1 log of e. And what is the log base 10 of e anyway? I don't know. Probably an irrelevant question, but I'll just do it anyway. 0.43429. Yeah, likely not something that comes to mind as something that I'd remember. Okay, so that's number 2. Now we'll try number 3. Y is log base 2 of 3x. So y prime would be 1 over 3x log base 2 of e times 3. And then I'd probably rewrite that as 1 over x log base 2 of e.
So when the problem is 3x problem, or the 4x minus 3, then when you're taking your derivatives, you do it in respect to x.
Yes.
Okay. If there's not an x in the problem, then you do it in respect to u.
No, you're doing it with respect to you. When I do the problem, I'm doing it with respect to you. But there's no u, so I have to do it with respect to x. Yes, Joe?
Can you explain how you do that, please?
Yeah. So I'm looking at the book where it's telling me the formula, and it says the derivative of the log is 1 over the argument times log base 2 of e times the derivative of the argument, which is 3. Those 3's cancel out. I get 1 over x. Now, if I wanted to, I could also recall that log base 2 of e, log base 2 of e is the same as log e divided by log 2. Remember that from a long time ago? Which is also natural log e divided by natural log 2. Now, natural log e is 1, so that'd be 1 over natural log 2. So we could write this if we wanted to. We could say it's 1 over x natural log 2, and that would be just as good. So if we wanted to do that, I don't want to do that, but we could do that if we wanted to. We wanted to hose over the instructor on some test to see whether or not he can count my problem as right form. Y is equal to log base 7 5x plus 2. Okay, so I'm looking at the go by again. Y prime 1 over 5x plus 2 log base 7 of e times the derivative of 5x plus 2, which is 5. So I would rewrite that as 5x plus 2 log base 7 of e.
How are you able to solve the derivatives quickly? Is it just something that you personally remember, or?
Well, it's on the previous page. I remember it from the previous page. There's nothing about common logs that I remember from the last time I did
No,
this.
that's the derivative.
But the derivative of the natural log is something that's so simple, I remember that one. And we use it
Like
often.
the derivative of 5x plus 2.
Yeah.
The derivative of that, how is it that you know that it's 5?
Okay, well, if you spend if you have, how many children do you have?
Me? 1.
One, okay. Well, I had 5 children that went through calculus in high school, 10 years apart between the oldest one and the youngest one. I'm a math major from Michigan State, and I have a master's degree in math from UNO, and I have the back of the book to look at. So given the back of the book to look at, I see that the derivative of some function to the n is equal to n x to the n minus 1. And I see that some function some function dxcu is equal to c du dx. So I see a number 4 there. And I look at those guys and I say, okay, well, that means the derivative of 5x plus 2 is 5. Also, I know that if I had a line that was y is equal to 5x plus 2, that 5 is the slope of the line, and the derivative is the slope of the line. So that how many? So that was 4 children, 2 degrees from 4-year universities, the back of the book, and the slope of the line from a previous chapter. How's that? Is that enough? That's how I know. All those things I know. Yeah. All right. So now we get to the easy ones. Number 5. So for those that did something weird, like came to every class from Tech Math 2 on, then it wouldn't be an issue for you, Bill. Yeah. Yeah. Uh-huh. Yeah. Uh-huh.
I got my
Okay.
work schedule fixed now, so.
All right, so that's fine. Yeah, that's fine. Y is equal to natural log. Okay, so now we have natural log things. So this is going to be better. 2x cubed minus 3. So y prime is going to be something over 2x cubed minus 3. And what goes on top is the derivative of that, which is going to be 6x squared.
Do you have log natural after that?
Definitely not.
Why not?
Look at your formula. Look at your formula on page 776. It just says 1 over u du dx. Yeah. Now, ask yourself, what is the log base e of e? 1. So you could have done that, but if you did, you would have gotten 1, and it's not, and so what?
So then you wouldn't count it wrong then if there was log e.
Yes, I would, because it's not part of the form.
Well, it's equals to 1, so you're just multiplying by 1 so you get the answer.
Still not part of the form.
The answer to the problem is not 1. That is just a part of it.
Yeah.
Yeah, if you put log base e, I'd mark the whole thing wrong. Because I'm that type of guy. Number 6. Y is equal to natural log x squared minus 4. So y prime, x squared minus 4 goes on the bottom. The derivative of x squared minus 4 goes on top. 2x, and I'm done. Number 7. Y is equal to the natural log of the tangent of 3x. All right, well, clearly this isn't going to work very well. Y prime is equal to 1 over the tangent of 3x. And now I'm going to have to come up with what the derivative of tangent 3x is. So we move back 2 sections and find that the derivative of tangent is secant squared 3x times the derivative of 3x, which will be 3. Okay, so my final answer would look like 3 secant squared 3x divided by tangent 3x. And then I'd ask myself, can that be simplified any? And I'd probably say, I really don't care, I'm done, and that'd be good enough. All right, so there I had to leave the section of the book to find the answer. But I could have looked at the front cover. That would have worked. Oh, another one, same type of thing. 8. Y is equal to the natural log of the secant of x squared. Okay, so y prime would be, on the bottom, we got the secant x squared. Now I need the derivative of the secant. So I'll look in the front and the back cover for that one. That way I don't have to fumble around. The derivative of the secant is secant tangent. Okay, so I'm going to have secant x squared tangent x squared. The derivative of x squared would be 2x, and I'm done. Right.
You cancel out the secant x squared?
Oh, yeah, I guess I can.
But do you have to cancel out the secant?
Yes, definitely.
Would that 2x come from the derivative of
x squared, right? That's where it came from.
So in the last problem, you would probably get rid of your 3x's then?
Were there 3 x's there?
3x over 3x.
I don't see any 3x over 3x. Where do you see it?
3 secant squared,
Yeah.
3x over tangent 3x.
And which one of those get canceled out exactly?
I don't think you can do that though, because it's the because you can't cancel exactly tangent and secant can't cancel each other out.
Good try. Yeah, this is all one thing. Right? This is all one thing. This is all one thing. Those are two different things. Nothing can be canceled out there. All right, good enough?
Good.
Good try, Dustin, to try to
G-double-O-D.
try to confuse the instructor. I know.
I tried confusing myself.
Yeah,
That's
try
my
to
strategy.
confuse yourself. Yeah.
Okay, great.
All right, so y is equal to natural log x sine x. Okay, now remember that if I take the derivative of xy, that's going to be xy prime plus x prime y, right? So that's what I'm dealing with there. So y prime equals, and on the bottom I've got x sine x, and on the top I'm going to take the derivative of x, so it's going to be sine x plus x cosine x. Good enough?
The
I
x
got-
sine x on the bottom all one thing, or can you cancel out the sine x's?
You can't
What
because
sine
it's
x?
addition on the top.
Okay.
I got an addition there, yeah.
Okay.
Like terms.
Okay.
So you could write it, I would leave it the way it is, but you could write it 1 over x plus cotangent x. You could write it like that, but that would show a certain amount of anal perversion, probably. You know,
Eric likes that.
I mean, something. You know, you obviously something. You would have to question your parenthood if you took a perfectly good answer like that and changed it into something like this, right? You know, what planet did you come from? We'd probably have to ask that, right? Yeah, so we'll just get rid of that idea altogether. There's no reason to take a perfectly good thing with sines and cosines in it and tell me the final answer is a cotangent in it. You know, there's no good reason to do that. All right, number 10. Oh, number 10 looks cool. About time we start getting some reasonable problems around here. Y is equal to natural log x cubed cosine 2x. Now these particular problems are cool because you test a whole lot of different things at the same time, right? X cubed cosine 2x. So I'm going to have 3x squared cosine 2x minus 2x cubed sine 2x. So I took the derivative of this guy, 3x squared times that guy, and then I kept this guy and took the derivative of that guy, which is going to be minus sine, and then I got to take the derivative of 2x, put the 2 up there. And again, I wouldn't rewrite it from there and get, in this case, I can have something that has tangent in it, but I wouldn't take something perfectly okay with sines and cosines and on purpose putting a tangent in it.
Could you explain this one just a little bit more?
I doubt it. I mean, okay, so I'm going to take the derivative of natural log, whatever the argument is, it goes on the bottom. I put it there. The derivative of 3x is 3x squared of x cubed. X cubed is 3x squared times what I got left over. Then I keep the 3x squared. I take the derivative of cosine 2x. The derivative of cosine is minus sine 2x times the derivative of 2x. That gives me that too. Okay, so I leave enough room in my when I write it down to add things front and back as I need them. Right. Number 11. Y is equal to the natural log of 3x minus 2 to the 1/2. I would never write it down originally with a square root in it, although my final answer will have a square root in it. Y prime equals. Okay, so on the bottom, I'm going to have the square root of 3x minus 2. Okay, and then I got to take the derivative of the arguments. That'd be 1/2 3x minus 2 to the minus 1/2 times 3. Okay, then I'd rewrite that. Y prime is equal to 3 divided by 2 3x minus 2. Oh, that was bad. Okay, so the rule says if y is natural log u, u prime is 1 over u du dx. All right, so 1 over whatever the argument is, I write it down there. I then take the derivative of this guy, 1/2 3x minus 2, 1/2 to the minus 1 would be minus 1/2. Derivative of the inside would be a 3.
Explain how you got the derivative of 3x minus 2
If y is equal to x to the n, then y prime is n x to the n minus 1. So if y is equal to x to the 1/2, then y prime has to be 1/2 x to the 1/2 minus 1, also known as 1/2 x to the minus 1/2. Exactly what I did there. And then I see I've got square root of x minus 1 squared because I have it twice. I got it there and I got it there, so I can take it out there. Yes?
So then the final answer would be that one right down the bottom.
Yeah, that'd be good. That'd be a good final answer. All right, we'll do 38. We don't have to do 38, but we'll do 38 and say, okay, we did 38. And y is equal to the tangent of the natural log of x. And I want to find find the equation of the tangent line at the point given. So I want the equation of the tangent line at point given. And then x is equal to 1, x is equal to 1. Okay, so that's what I want to do. All right, so if I find y prime is going to be, what is the derivative of tangent? So I move back, and the derivative of tangent is secant squared natural log x, okay, times the derivative of natural log, which would be 1 over x. Okay, so y prime at 1, this is going to be the slope of the line. Slope of line. All right, so that's going to be the secant squared of the natural log of 1 times 1. What's the natural log of 1? I think it's e, right?
Yeah.
1 natural log, no, it's 0. The natural log of 1 is 0. So natural log of 1 is 0, and the secant looks like that. So the secant is 1 at 0. I square root it, it's 1. The whole thing is 1. All right, so the slope of my line is 1. Slope equals 1. Now we need to know y at 1, because we need to know the point x, y. And so the point x, y is going to be 1, y of 1. Okay, so I already know y. So what is y at 1? Okay, so the tangent of the natural log. What's the tangent at 0? The tangent at 0 is 0. So the point I have is 1, 0. That's the point that this guy is going through, and the slope is that. Okay, using the point slope formula, y minus 0 is equal to the slope 1, x minus 1. So y is equal to x minus 1. That is the equation of the tangent of the curve. Y is equal to the log of the natural log of x at x equal 1. They just love it. Now that is something you're going to be asked to do over and over and over again in your Calculus 1 class. Find some weird ass equation, find the whatever, given the whatever. That's going to be. And is that pretty weird? I mean, on the weirdo meter, is that pretty weird? The tangent of the natural log, yeah, that's pretty weird. I don't ever recall having a real problem having a solution that is tangent of the natural log. And that just totally blows your mind. Okay, good enough? All right. Now I got to go back and re-edit this thing to get all this profanity out of it, right? Well, wait a minute. Well, maybe not. Wasn't that bad, was it? We'll just